Hi, welcome back to Kirsty's virtual classroom. Today in California geology, we are talking about the San Andreas Fault System. So prior to 1906, nobody really knew much about the San Andreas Fault or that it even really existed. But in 1906, San Francisco suffered from a massive earthquake that was a 7.8 on the Richter scale. And before that, nothing had really affected people in the area. This fault has about a 100-year recurrence interval on it, so there's a massive earthquake approximately every 100 years or so. And this earthquake was one of the many that resulted from episodic displacement along the fault throughout its life of about 15 to 20 million years. So this fault isn't super old, but not a lot was known about it. We didn't know what type of fault it was. We didn't know what kind of damage it could actually produce. So scientists, after this earthquake in 1906, started to really do some investigating and trying to trace the fault and figure out just how impactful it can be to California. So today we know that the San Andreas Fault System is a right lateral strike slip fault, and that it is about 1,300 kilometers long. It is composed of several active segments and parallel strands, so it has a lot of offshoots and different faults that kind of radiate from the main fault line. It does mark the boundary between the North American and Pacific plate, and some parts of the fault are parallel to that boundary and some are kind of oblique. So just depending on where you are along the faults, we do have the big bend that happens just after the transverse ranges in Southern California. So as we know, in California and Nevada specifically, we have a lot of faults, and a lot of those faults are producing earthquakes, some on a regular basis and some are more on the dormant side. The Sierran block is actually fairly rigid, and it doesn't have a lot of faults within it. So this is the Sierran block right here, but it has a lot of faults around it that do cause it to move. So plate boundary movement is distributed over a wide zone and many faults in California. So in the Bay Area, these are the primary faults that we see. So we do have the main San Andreas Fault System running through the Bay Area. And then we also see the Calaveras and the Hayward are two heavy hitters in the area. Green Valley, Greenville, San Joaquin, Rogers Creek. All of those are part of the San Andreas Fault System, and they move similar to the San Andreas Fault, but they're sort of offshoot faults. So the San Andreas Fault relative to San Francisco, you can see this is San Francisco here, the bay, and this is a false red image, and this is the fault running through here, and you can kind of see the ridge, the linear ridges that follow the fault. And that's from the grinding between the Pacific plate and the North American plate as they slide past each other. So housing, obviously, is really difficult along fault, especially a major fault zone like this. And prior to the 1906 earthquake, people were building a lot and not knowing that they needed to build to accommodate such a massive fault system. So in the early 1900s, we saw a lot of development basically right on the fault because they didn't know any better. But in California, we see a lot of seismicity. So each of these orange dots is seismicity along a particular fault. So each of them is its own epicenter, and there are a lot of them, as you can see. This up here towards the north is where we see the triple junction between the North American plate, Pacific plate, and the Juan de Fuca plate, And then all of this seismicity is only between 1977 and 1996. This is not recent data necessarily, but it's just a snapshot to kind of show you just in those few years how much seismicity we see in California, especially compared to neighboring states like Nevada. So if we look in like northeastern Nevada, there's not nearly as much happening as there is in California. So we see constant slip in some areas along the San Andreas Fault. In the areas where we see a lot of serpentinite, it allows for more slip. So serpentinite is very slippery. It's an asbestos-bearing rock, and it allows for the fault to move slowly. And that kind of creates a better situation than in areas where it is gridlocked by stronger rocks. So rocks that are stronger, like in the transverse ranges and the peninsular ranges in Southern California, it gets kind of gridlocked. And so there's not a lot of slip that occurs. And what's going to happen eventually is it'll build up so much energy, it'll finally break through those rocks, and it'll slip in a great way and cause a very large earthquake. But the constant slip creates some nice low landforms, like these low-lying coast ranges that we just talked about. So here in the Carrizo Plains specifically, we do see a very nice, because there's not a lot of vegetation in this area, creek offset. And that also gives us a really good indication of the slip motion that we see, what type of motion, which way the fault is going. So the ridges occur parallel to the fault trace, and then this creek is offset. So this ridge, which is the red line, is offsetting this creek. And as you can see, if you stand on this side of the creek, it is offset to the right. So it indicates this is a right lateral strike slip fault. So that's one of the many ways that we tell what type of fault we're looking at. And then we do see a lot of sag ponds along the fault, which are areas that kind of get depressed and then water fills in. So northern San Andreas Fault in the Mendocino Triple Junction area, where the Juan de Fuca plate lies, it gets a little bit more complicated because there is the addition of a divergent plate boundary and a subduction zone. So the San Andreas Fault joins the remnants of the Farallon plate, or it's now known as the Gorda plate, which is a subplate of the Juan de Fuca plate that is still subducting beneath North America along the Cascadian subduction zone, mostly in Oregon and Washington. So this is the San Andreas Fault leading up here, and then it kind of joins this Mendocino Fault zone and the subduction zone. So it kind of disappears to the north here. We don't see it a lot in the Klamath, Eureka area. But in the Bay Area, it's predominant. It's really active. I see a lot of motion on a regular basis. So here's a snapshot of what occurs. Most of what is further inland is creeping. So a lot of if you look back at our Coast Range PowerPoint, you can look at the geology here, and a lot of this is where our serpentinite lies. And so we see a lot of creeping in this area, kind of East Bay. And then out in the ocean and in the actual bay, we see much more much more locked movement. We don't see as much motion in that area because of the rock that is there. The rock that is there is much more interlocking and kind of doesn't allow for that slip to occur. So the earthquake probability maps are obviously fairly high for anything along the San Andreas. But to give you an idea, the San Francisco Bay Area has an earthquake probability of 62% of probably one or more magnitude 6.7 or greater earthquakes between 2003 and 2032. So we haven't really seen anything that high in this time period. We're obviously in the middle of this time period right now, but we saw something in 89 that was fairly high, but we haven't seen anything lately. So hopefully this projection is on the higher side and we don't see a massive earthquake in this time period. But to be prepared, there are engineers and geologists working together to make sure that all of the buildings and everybody is equipped in the region if this happens. So unlike 1906 earthquake in San Francisco, We are much better equipped nowadays with our building safety, our construction, and our engineering, and we know a lot more about the geology. So all of that combined, we are much better prepared for this, but we also are not 100% sure when these things happen. We cannot predict earthquakes at this time. We see precursors, we see earthquakes, small earthquakes that happen before a larger event occurs, but sometimes those small earthquakes happen and then nothing else happens. So it really just kind of depends. It's not a black and white scenario. So we create these probability graphs just to kind of help prepare people, and then hopefully nothing too devastating occurs. So the creeping segment, which isn't as likely to create such a massive earthquake, is where we see a lot of movement on a regular basis, but they are very small earthquakes. So we don't see a lot of locked zones, and the slip occurs basically daily. A lot of times we see maybe up to like magnitude 4 earthquakes, but they happen so frequently that energy is all being released. So remember, this is all about energy and buildup. So if the rocks don't move and the faults don't move, they're going to move eventually. And it just depends on how much energy they're building up. If we build up too much energy in these rocks, then eventually when the rocks slip, the energy is all going to be released and it's going to be high, which is going to create a lot more ground shaking and the magnitude will be higher. But if this energy is released on a regular basis, it will move in small increments and then we won't see this real big earthquake occur. So we move down further south. Now we're looking at the Big Bend. So this is as we move through the transverse and peninsular ranges. So there are a lot of offshoot faults here. The big one being the Garlock Fault that runs basically perpendicular to the San Andreas Fault. We have a lot more faults in this area, and we've talked about some of them as we've moved through the different ranges of California. So here's a look at the Big Bend and what the slip rates look like. The red line is fast compared to the other faults. So the Garlock Fault is probably the next fastest after the San Andreas Fault here. And then some of these other guys don't move nearly as fast. Some are almost dormant. And this is obviously going to be an issue if these rocks ever release the energy and slip in the Southern California area, because it's going to create a very massive earthquake. Here's a look at some of the earthquakes that have occurred. So the deep earthquakes are associated with subduction zones, and then transform plate boundaries generally have shallow to intermediate depth earthquakes. So most of these are actually fairly shallow. We're not seeing a whole lot of intermediate or deep earthquakes at this time. So when we look at the bend, or the Big Bend in the San Andreas Fault, we need to understand that when this occurs, a lot of times it kind of creates this separation of the fault, or what we call a stepover. So in a right lateral fault, if we have a left stepover or a right stepover, it will create either a restraining bend or a releasing bend. So in a left stepover scenario, where it is stepped over to the left, essentially, just like when we're trying to figure out if it's a right lateral or a left lateral, it creates a ridge between the two fault segments. So we see ridges and folds that are bound by these thrust faults that are generated by the stepover that is created between the slip between the two fault lines. Okay, if it's a right stepover, so the stepover is to the right, we start to see a depression. So we see basins and depressions where normal faults are being generated between this strike-slip fault. Okay. So looking in the Southern California Big Bend area, here's the Great Valley, San Andreas Fault, here's the bend, and it does bend a little bit again down as we move into the Gulf of California. So it's kind of an oblique view of the fault. Okay, here are the areas where we do see stepovers. So this is in Southern California, almost to Baja California's bend. Okay, here's another look. We've got the Pacific Plate here, North American Plate. This is where we see a lot of thrust faults. So this bend here, this first one near the Los Angeles area, is where we see a lot of thrust faults being created. And here's another look at that. So we have the Pacific Plate here and the North American Plate here, and they're kind of almost colliding in this area. So it creates because of compression, the reverse faulting at this Big Bend area. Because they're not exactly sliding past each other 100%, they're colliding in a slight oblique angle. So let's talk a little bit about the 1906 San Francisco earthquake. This happened on April 18th, 1906 at 5:12 in the morning. It was a magnitude 7.8, and the location was nearly 300 miles of the San Andreas Fault that ruptured. So it produced a very strong shaking along coastal Northern California and most intense in Santa Rosa and San Francisco. The earthquake not only generated massive ground shaking, but it also ensued some fires and it killed approximately 3,000 people. So here's kind of a look at the aftermath of the 1906 earthquake. There's many more images out there, but some of these are very devastating to look at because most, if not all, of their buildings had some sort of repair that needed to be done, or they completely lost the building. Here's the St. Francis Motel. If you've ever been to San Francisco, you probably know where this is, but it gives you kind of a look at how much damage there was. So then we have the Loma Prieta earthquake. This happened in 1989 on October 17th, around 5:04 p.m. This was a magnitude 7.1, so very strong, and it kind of gives you a look at how much was affected. So here's the San Andreas Fault Zone. This is the epicenter here, and this is the focus at depth. So we're looking at just south of the San Francisco Bay Area. So here's a look at some of that displacement. So clearly a lot of the surface features that we see offset really show us that sense of fault motion. So it's always disheartening when they make a movie called San Andreas, they get the fault motion wrong. So if you watch that movie, there's a scene where they're at a gas station and there's a big trench that opened up, which that doesn't really happen, but regardless, there's a big trench that opens, and then you can kind of see the offset in the image, and it's offset to the left, not to the right, which is so sad because they did have a consulting geologist, but I digress. So the San Andreas Fault obviously creates a right lateral strike slip motion, and that's viewed in this image. So if you remember from faults and earthquakes, when I taught you how to figure out what type of fault you're looking at, if you're driving down a road like this one and you're in a car and you have to turn your steering wheel direction along the fault to get to the rest of the road, you have to turn right slightly here, right? So the fault runs through here. You're driving this way, you have to turn right just a little bit. So here's some Loma Prieta damage. The area was not as equipped as they are today as far as earthquake safety and precautionary measures that they take in the event of an earthquake, but it did cause quite a bit of damage in 1989. So the Freeway is one of the most famous images from this earthquake. It had some of the most deaths of any particular location. So there was about 42 of the 63 deaths occurred on this bridge from this collapsed freeway. Here's another look at the collapsed freeway. Obviously, the engineering here failed fairly significantly. Here's some more damage. The Bay Bridge did take some damage as well. So here's a look at the map and kind of the magnitude, intensity, the shaking that occurred. So the most extreme was in Loma, Prieta, and then obviously it radiates from there, right? So the further you are away from the epicenter, the less ground shaking you will feel. So after the 1989 earthquake, there was still a lot of seismicity that occurred for about a month. So the main shock was the 7.1, and then from there we still saw quite a few earthquakes in the area as things kind of settled down. So remember, there's going to be foreshocks and aftershocks of any earthquake, and just kind of depending on the motion and how much energy is released, you might see more or less. So seismicity is not necessarily constricted to just the 2 times that I talked about. There is a lot of seismicity that occurs. Some of it is small, and then those 2 very large ones are some of the largest in California's history. But in the Big Bend area and this LA area, we have seen a lot of seismicity as well. So we do have some recurrence intervals listed here. So those are the average number of years between ground rupturing earthquakes at key sites that we've looked at. So most of it is the 100 to 150 year interval, but we do see longer. So in the Southern California area, it's a really long time since we've seen very historical ground rupture. So that's what leads a lot of scientists to believe that they are in for a large earthquake in the near future. So here's another look at the northern portion. So towards the center, obviously we have closer to the 100 to 150 year kind of recurrence interval. Towards northern and southern, we see it shrink. So in the northern area, we do see more locked rocks, a locked situation where there's not a lot of movement occurring. And we are approaching in this area the triple junction. So there's more complicated movement occurring here. So it could be because of that interaction. There is a lower chance of a very large earthquake occurring from strictly San Andreas Fault slip movement. So, as I've talked about before, we cannot predict earthquakes. There are many theories about how we can, but we just can't do it yet. So we have things that kind of tell us, well, maybe something's going to move here pretty soon, but we just don't know. It's really hard to make predictions on things like this. I know a lot of the public thinks that it should be done or can be done, but it can't. Nature does what it's going to do. We can make, graphs and all these pattern recognitions based on what we've observed so far, but we're not there yet. So we use historic data and we try to prepare people by giving these predictions, like there's maybe a 67% chance that this will occur between this 20-year time frame. But if that doesn't happen, it doesn't happen. So, or maybe it happens earlier, or maybe it happens twice. We don't have enough data. We will never have enough data, in my opinion, to actually predict earthquakes and pinpoint an exact day or even a year or a time for that matter. Earthquakes only happen for 10-15 seconds, and trying to pinpoint that down to an exact time frame is really difficult, especially when they only happen every 100 years or 300 years. So keep that in mind when you're learning about earthquakes and talking to people in the future. We cannot predict them, and we more than likely will not ever really be able to predict them down to the second they will occur. So there's going to be one now. No, now. Okay, maybe now. All right, there's going to be one now. Okay, now. It's really, really hard. It's probably never going to happen, especially in our lifetime, being able to predict earthquakes or volcanic eruptions for that matter. All right, I'll catch you guys in the next video. Bye.